Hey, welcome to our daily training. I'm Dave Greenhack with Hurley Engineering, and I have Daryl McLaughlin. This week, he's giving us training on heating systems and hydronic principles of design. So, with that, I'll turn it over to Daryl.
All right, thank you, Dave. We started off yesterday talking about basic piping arrangements that we use in most hydronic heating systems. Basically, the primarily the difference between primary secondary systems and with relation to variable primary or primary only. And so we're going to start there again today. Let me share my screen so we can get moving along here. There we go. All right, and can you guys all see that now?
Yes, Daryl.
Got it.
Yep.
Okay, good deal. So I'm going to back up for 1 second because I think yesterday we kind of left off after talking about the basic system piping arrangements. And I wanted to go back and make sure we had talked about this, the uh, direct return versus reverse return. So the drawing on the left here is going to be uh, a direct return system. So basically, as the fluid goes out, we go through each terminal or heat emitter in our system. Again, this could be a chilled water system as well, not just a heating system. And then we come back. So in this type of arrangement, we have different head loss through each different branch of our piping tree here. And if we don't account for balancing this with either valves or control valves or pumps or something along those lines, we're not going to have equal flow through each of our branches. In the system to the right here, this is a reverse return. So what we're trying to accomplish here is the first unit that we arrive at on our flow will be the last one out on our return. So here we're the first one in, the fourth one out. The second one would be the second one in, and the third one out. Then the third one in, second out, fourth in, first out. And by doing a reverse return like that, it's self-balancing. We equalize the head loss through each of these branches, and we can essentially self-balance our system that way without using valves and additional pumps. So just keep that in mind as you're in mechanical rooms and boiler rooms. If you see arrangements that look a little outside the norm or uh, overly convoluted, it might be something that they're trying to accomplish a reverse return and balance the plumbing. So, okay, so I wanted to move back. We kind of left off here yesterday talking about primary, secondary, but I wanted to talk about how that relates to systems that we're going to start seeing more and more of, hybrid systems that might use a combination of different technologies like heat pumps and condensing boilers, or potentially condensing boilers and non-condensing boilers. So, and let's talk about first, well, before we get there, let's talk about a non-condensing application. So one thing to keep in mind is when we're running this system here, we've got a non-condensing boiler. We can run this at any temperature available to that boiler. So we can run 100-degree set point. We can run 180-degree set point. Now, ideally, we'd rather be below 140, or at least keep our exhaust gases below the dew point so we're condensing. That's where we'd like to be. But if we have a non-condensing boiler, like is shown in this slide, now that temperature range of set points is not available to us. The reason being that if we run below certain temperatures and that boiler begins to condense, that condensation is corrosive, and that boiler is not built to handle that, and it will be detrimental to the long-term reliability of the equipment. So whenever we're running non-condensing boilers or in a non-condensing application, we need to protect this boiler from getting cool enough on the returns such that it could cause it to condense. Now here, this is a straightforward way where they're not showing on this drawing. If you look at this three-way valve, we're not showing how it's controlled. It could be thermostatically controlled. We could have sensing bulbs and actuators, and there's many ways you can control this three-way valve. But the basic point is we have a three-way valve to protect this return water temperature. And you can see at 130 degrees is what we're trying to stay above here. If we were to go below that, this three-way valve would begin to stroke, and our outlet water from the boiler would be recirculated back to the return to keep our return water temperatures above 130 degrees. So nothing else in this system has changed. We've still got our standard primary, secondary. We're still pumping away from our point of no pressure change. We're still monitoring our temperature set point here downstream of the outlet of the boiler. So, but we've just added this three-way valve to protect our return temperatures to make sure that we can operate this without going below temperatures that would damage the equipment. Any questions on that? Okay. So now we're going to introduce the next one here. So this is our first step into hybrid systems. Here we've got a non-condensing boiler as well as a condensing boiler. So um, before we talk about exactly how the system's laid out, let's talk about some of the, I guess, the rules of engagement for hybrid systems like this. So anytime we're doing a hybrid system and we're going to have a condensing and a non-condensing piece of equipment, we've got to have the condensing boiler upstream of the non-condensing boiler. Okay, that's rule number one. Two, we've got to have the control, the temperature that we're measuring downstream of both boilers. Now that's true for most heating applications, but it still holds true to hybrid applications. Our control is still going to be, if you'll follow my cursor, this point downstream of both of them. And we have to monitor that mixed or common temperature. Then ideally, our control would also prioritize our condensing boiler. So that's to gain the efficiency, to have the benefit of this condensing boiler, we want to prioritize it at all times. Fourth, we want to protect our non-condensing boiler, just like we talked about. Just because we're running a condensing boiler in here doesn't allow us to start running this one in condensing temperatures as well. So we still have to have concern and protect the temperatures being introduced to the return of the non-condensing equipment. And then last of all, we're going to have an outdoor air temperature component to this usually. So we're going to reset our temperatures and usually run lower when the temperature is cooler outside. And I'm sorry, run lower temps when the temperature is warmer outside and higher temps when the temperature is cooler outside. So the first thing we're looking at here is that both of these boilers are still plumbed in a primary secondary arrangement. So the flow in this loop is completely independent of all the other pumps in the system. And the flow in the non-condensing boiler loop is independent of the flow in all the other loops. So we're able to control the temperatures that are going to there and prevent non-condensing temperatures if possible, or condensing temperatures. The other thing we're doing is we're putting this by putting the non-condensing boiler in front, putting the condensing boiler in front of the non-condensing boiler. We're able to preheat that water and now introduce warmer temps into the condensing boiler, or the non-condensing boiler. Sorry, I'll get it right here sooner or later. So we're going to run this non-condensing boiler, or we're going to run the condensing boiler as much as we can. So even in the coldest times of year, we're still going to run this boiler first, and we're going to use it to preheat the returns that's going here. So we're just using the non-condensing boiler to increase our capacity for heating in the system.
Hey, Daryl,
Yeah.
would you mind explaining why we have condensing boilers and what's the advantage?
So it's primarily efficiency. So the cooler we can run any heating system, the more efficient we're going to be. So now that all relates to if we can get our return temps cool enough, then as they come back into the boiler, it cools our exhaust gases to the point where we drop below the dew point, and the moisture in there begins to condense. And once we get to that point, we'll capture all that latent energy that's still in our exhaust gas, and then we can get that energy and put it back into our system instead of out through our stack, right? So just by having a low mass boiler and better combustion equipment, we can gain certain efficiencies. But the big jump in efficiency in boilers is capturing that latent heat, and that only happens when you get below the dew point and start condensing the moisture in the flue gas. So ideally, too, we'd like that to happen inside the heat exchanger, right? So it could happen right at the outlet. It could happen in the stack, depending on where you get to that point and you're below the dew point. But in a condensing boiler, we'd like for that to happen in the heat exchanger so we can capture all that heat, put it into our heating medium, and pump it back out into our system instead of out of our exhaust stack. So,
Great, thanks for that, Daryl.
so that's the primary function of this. We're going to run this condensing boiler is going to be our primary heating appliance, and we're going to try and capture all the efficiencies we can out of that, and only use this non-condensing when we need additional capacity for our system on the cold days. Let me go to the next slide here. So now you can see we've added two boilers. And we bring this up because one of the other benefits is, everything is associated with the cost. Traditionally, and still to this day, condensing boilers are going to be at a higher price point than non-condensing boilers. So maybe the people we're working with don't have the budget to replace all of them with condensing boilers, but they can do two. Well, we can still give them a system that gives them much improved efficiency for 75, 80% of the year. And then there's only 20% of the time that they might have to run some of these non-condensing appliances. But even if we put multiple boilers, we're still following the same basic principle. We've still got a primary boiler loop here and a primary boiler loop there, right? And so we're using the outlets from our condensing boiler as the return for our non-condensing boiler. I want to get to the next one. Sometimes even you can see here, we've got triple duty valves. So we're balancing this flow through here to make sure we have the flow we'd like. But you can even do these primary secondary setups with a reverse return as well, just to make sure you have flow balance through the equipment. So here's our first introduction to adding a heat pump. So a heat pump is the same thing. So technically, even though this is a condensing boiler, the heat pump is considered our more efficient appliance. So we're going to put it upstream of the condensing boiler. Fewer emissions, better efficiency, and then lower carbon footprint if that's the concern for your environment, your area. So we're doing the same thing though. It's still a primary secondary setup. The heat pump operates on its own loop and it discharges fluid into the returns of the condensing boiler. And we're going to prioritize its operation. It's always going to run first. It's going to be our lead appliance. And our lag appliance will be the condensing boiler in this scenario and only come on when we need the additional capacity. And this one, I believe, is going to become much more common. We're starting to see this already in our area. So, and this is a air to water heat pump too, by the way.
Yeah, I'll add a couple notes on the heat
Yep.
pump and this hybrid design. So same concept, you put the more efficient appliance upstream and it does the primary duty. Now, heat pumps, um, it's ironic because the colder it gets, the worse they get. And that's when you need the most heat. So we talk about the ambient temperature and how we'll, designate the appliances and what does what and how hot we're going to make that water. Well, during mild temperatures, so think, mid 40s, heat pumps are super efficient. You can get a lot of output for, very little input. And they can typically handle the entirety of the load because it's not that cold outside, and so the building doesn't need as much heat as well. Plus, they do better when it's not that cold outside. So that's when you're going to be running those. So it's kind of like they've just taken the heat pump's taken the place of the condensing, and the condensing boiler is taking the place of the non-condensing, same scenario, but slightly different operating conditions. Thank you.
Right. And it's important to remember too that just because we get colder and the capacity of the heat pump is reduced, we don't just shut it off and ignore it. We're still going to run it. If we only get 10%, 20% output, that's 10 to 20% output that we didn't have before, right? And it's still a benefit to the system overall.
Yeah,
So,
thank you, Daryl. In fact, you can designate the temperature it runs at. It can be at a less hot temperature because that helps the heat pump, less lift on colder days. You can do less hot, and that condensing boiler can take care of the rest. Um, it can feather up and handle extra temperature requirement, and they can work together that way.
okay, let me move on to the next slide here. So now here we've got a heat pump with a swing tank. So, and this is actually a potable or domestic application here. So, um, we're calling it a swing tank. It's stored energy. It serves the same purpose as a buffer tank in many scenarios, right? So, what we're really trying to avoid is short cycling of our heat pump equipment. So, if our temperature is small, we don't want small changes in the temperature of our output to cause the boiler or the heat pump to come on and off. So, we've got a reserve storage of heat capacity in this swing tank so that as our temperature drops, we can serve that load with the water that's already been stored and not have to turn our heat pump on every time our temperature drops a little bit. And it's the same principle we have in heating systems that use boilers. So if we have a system that has low mass and there's not much volume to it, we could have the same issues where we short cycle our boiler and our heating equipment. And in that scenario, we'd use a buffer tank as a swing tank to add more capacity to our system. So here I want to show this one. This is a hybrid like we've already talked about. It shows the heat pump being our primary upstream appliance. And then we've got two condensing boilers downstream of the heat pump. But I wanted to point out here, like we had talked about earlier, if you'll look, the primary loop for the condensing boilers is actually plumbed in a reverse return scenario. So you can see our returns are coming back, and this was getting the first return in, but it's the last outlet, last supply out to the manifold. So and that's done to try and self-balance these two and keep the flow equalized between the two. So let me move on here. So I think we've covered this here. This is some of the primary only. Let me get back, Dave. There we go. So primary non-condensing. So this is, we've talked about swing tanks and buffer tanks for condensing applications in primary, secondary. Here we've got a primary only setup, and we've got a buffer tank here for a low mass system. So just like we had a swing tank on the heat pump, we're using a buffer tank to control the swings in load on this system. So again, we've still got our three-way, it's not a valve here, but we do have a bypass return to protect return temperatures to a non-condensing appliance, even though this is a primary only system. And then we can use these tanks oftentimes, like you'll see, as hydraulic separators. So we'll have one loop here and one loop here, and their flow does not influence the other. So even though this is a primary only, we're using it like a primary secondary with this buffer tank being a hydraulic separator.
Thanks for pointing that out, Daryl, because yeah, it's misleading. It is truly a primary secondary with that
Right,
four-ported buffer tank. And often there'll be a baffle. With our American Wheatley product, there's a deflector so that the flows coming in don't go straight across to out. And that's how we separate those loops hydraulically.
right. And so it's just, and we just want to be exposed to more and more types of systems that we can see. That way we're comfortable with knowing what we see when we go into mechanical rooms and boiler rooms, right? So
You can
this
also
is
tell the difference of primary versus the primary secondary because they have pumps on either side, right? So you have
correct.
the load pumps, but you also have the primary source pumps,
Absolutely.
source pump in this case.
So now when we get to hot water, it gets a little bit different, right? So this is same thing. We've got hydraulic separation. We've got a physical separation here. So this is our indirect method of generating hot water. And this heating appliance over here, this could be a heat pump if we had an air to water. Depends on how we do things, right? But as with any heat exchanger, we just need a hot side, cold side. We need a heat input, and then we're going to send that heat out to our tank or whatever we're trying to use that heat for. With Patterson Kelly, it's the duration water heater is our standard indirect water heater or heat exchanger. So
This could also be our Alpha Laval or SWEP gasketed plate heat exchangers.
absolutely. So this is actually a braze plate, and so that would be more to swept. But any heat exchanger there would do the job, right? So in this one, it does operate similar to a primary secondary. We do have separation, but we also, again, like I said, we have physical separation in the heat exchanger, not just hydraulic separation. But I wanted to point this out too, because we do have some applications where this can become an issue. So when we're using plate and frame on these type of, or raised plate heat exchangers in this type of application, you can remove more heat than intended and send it back to the boiler. So here we've got a condensing boiler. It's not an issue. We can drop these return temperatures on the hot side. Pretty cool, as long as we stay above our approach temps. But if this were a non-condensing boiler, then we have to be really guarded about what we do inside this heat exchanger. Because if we send too cool return temps, again, we risk damaging the equipment. So a lot of times when we get to this type of application, we might go to a shell and tube because we can control the delta T on it and control the return temp going back to the boiler. So here, this is the same system. It's just showing a more complex piping arrangement. When we have multiple boilers, we've got to manifold things on the both on the boiler side and the domestic storage tank side as well. So um, this is still labeled as indirect heating. So, and there's confusion on those terms sometimes, right? So this is a volume storage tank for water, but this is an indirect heating application. Now, if that heat exchanger were to be placed inside this tank, then that would be an indirect heating tank and not a volume storage tank. So in this application, it's an indirect heating application with a volume storage tank. And then the same thing here, we've got an indirect application with two volume storage tanks, and then the necessary piping to keep this all balanced, reverse return, primary, secondary, to keep all our flows consistent. So let me go one more. So this is just showing the hot water, and this is our shell and tube option often. So um, again, if we don't have to, if we only have steam as a heating medium, or if we have non-condensing boilers, then we would go to this shell and tube to uh, to heat our water, so that we don't have to worry about return temps back to our non-condensing appliances.
And I want to just add to what Daryl's saying about you can still control on a gasketed plate,
Yeah,
but they exchange heat so rapidly, it's difficult to precisely control it. You can lose control pretty quick, is what Daryl's
right.
pointing out. The other thing is the shill and tube, they're easier to clean. And these devices with the circulator pump are
Mhm.
easier to or or it prevents the formation of scale better than a gasketed plate. Would you like to add anything to that, Daryl?
No, that's true. So the gasketed plate or raised plate, it's a real concern. So if you run too high, it's time, temperature, and turbulence. And if you don't have those just right, you can foul them up or scale them up fairly easily on the potable side, where you have minerals and salts and things like that that will precipitate. So um, that's a concern for the amount of flow you have. There's a lot of things that go into the design of systems with brazed plate and plate and frame heat exchangers for potable systems. So um, at times the shell and tube can be a little bit of an easy button. There's they're a little bit easier to plug and play with. Um, but we see them more often in the low temperature or the low delta T applications, right? So we'll typically operate these at 20 to 40-degree deltas, and we might operate the raised plate like 60-degree deltas, depending on what our system calls for. So
So remember, guys, um, these lessons are meant to provoke thought and awareness when you're in those mechanical spaces, like the reverse return. Daryl pointed out. He says if it looks a little funky, maybe it's a reverse return, and now you know how that pipes. These slides, you can find them on the Patterson Kelly website, or just reach out to me or Daryl. But this is all about awareness, and hope you got something out of it. Daryl, would
right.
you like to add any last comments?
No, that's it. Yeah. Send me an email if you have any questions or you think of something later that just pops in your head. And we'll try and get everything answered. And if nothing else, we'll bring it up in the next video and make sure that every question gets answered. So there's no dumb questions, right? So
What's your email?
it's Daryl, Darrel at hurleyengineering.com.